Every wireless interface, cloud app, and seamless video call ultimately comes down to this: raw electricity and pulses of light moving through physical space. This is layer 1 of the OSI model, the physical layer. It is the literal foundation of your network, where binary data is converted into physical signals. When it's time to upgrade your infrastructure, you face a hard choice. Do you pay a premium to future-proof your cabling, or do you stick with practical, standard-speed gear that fits your current budget? It's a critical decision because physical bottlenecks are permanent. If you lay the wrong cables, no amount of brilliant software configuration will fix your throughput. On this chart comparing investment costs to network capacity, you face 2 risks. Underinvesting causes signal attenuation, dropping data and throttling speeds. Conversely, overinvesting wastes capital on massive bandwidth that your older infrastructure cannot actually use. The goal is finding the optimal path right through the center. You find that path by looking closely at your specific architectural constraints. If your physical layer is flawed, the most expensive routing software on the market won't save your network's performance. Let's apply this to the most common Layer 1 choice: copper Ethernet cabling. For years, Cat5e has been the baseline standard. It reliably supports 1 gigabit speeds up to a maximum distance of 100 meters. It is highly cost-effective, and because the cable itself is physically flexible, it is incredibly easy to route around tight corners and through narrow conduits. Then there's Cat6, which is marketed as the standard upgrade path to achieve 10 gigabit speeds. This matrix evaluates Cat5e against Cat6 across maximum speed, distance, crosstalk resistance, and flexibility. Cat6 has a major limitation you need to account for. Notice what happens to the distance metric. Cat6 can only sustain that 10 gigabit speed up to the 55 meter mark. Push past 55 meters and signal attenuation takes over. The cable physically cannot maintain the frequency, and your speeds immediately drop back down to standard 1 gigabit throughput. To understand why, consider crosstalk. This is when electrical signals from wires inside the cable bleed over and interfere with each other. Cat6 handles this internal interference by using a physical cross-shaped plastic separator running down the center of the wire pairs. But that separator introduces a trade-off. It makes Cat6 cables significantly thicker, stiffer, and much more difficult to pull through complex wall routing. Cat5e lacks that central spline. It relies entirely on how tightly the internal copper pairs are twisted together to manage interference at its lower 1 gigabit speed. If your cable runs are longer than 55 meters and you are expecting 10 gigabit throughput, paying a premium for Cat6 is a total waste of your budget. Of course, selecting the perfect cable means nothing if it's terminated incorrectly at the ends. There are 2 acceptable wiring standards for Ethernet ends: T568A and T568B. Choosing one over the other is mostly a matter of regional preference, or matching whatever your building already uses. The hazard comes from mixing them. If you wire one end of a cable using the A standard and the other using the B standard, you accidentally create a crossover cable. Crossover cables are useful if you want to connect 2 computers directly to each other without a router, but if you try to use one to link up standard legacy switches, the connection will fail. Most modern switches feature something called AutoMDIX, a software protocol that detects this wiring mistake and silently corrects the pinout for you. Older hardware lacks that feature. Mixing termination standards creates a hard physical barrier that legacy switches cannot bypass. Sticking to a single uniform wiring standard is the only way to guarantee a functional network layer across all your equipment. Now, let's look at what happens when you need to scale over much longer distances. That's where fiber optics become mandatory. The challenge is figuring out how to integrate this new long-range fiber run into your existing short-range copper infrastructure. This decision tree flowchart shows how to bridge media types. It asks, does your switch have an open SFP slot? If yes, you follow this branch. You use an SFP module, a small form factor pluggable transceiver that slides directly into your compatible switch. This is the ideal scenario. SFP modules offer clean, space-saving scalability. You add fiber connectivity natively into the switch itself, avoiding any external clutter. If no, meaning you have a legacy copper-only switch, you follow this branch to the fiber media converter. A media converter instantly bridges the gap between copper and fiber, but you are introducing a bulky external device, an extra power supply to plug in, and a brand new physical point of failure into your network chain. Media converters are a necessary band-aid for legacy hardware. But if you have the option, investing in SFP-compatible switches provides the only elegant, modular path forward. Ultimately, your physical layer choices have to be dictated by your distance requirements, your existing hardware, and your budget, not marketing claims. This matrix scorecard maps out the exact hardware combinations you need based on 3 distinct viewer archetypes. Let's find your environment. First is the home setup. If you are dealing with sub-gigabit speeds and tight budgets, stick exclusively to Cat5e. If your internet service provider isn't delivering more than 1 gigabit to your modem, installing Cat6 in your walls is a waste of money. Next is the SMB upgrader. For growing businesses, invest in Cat6, but keep those runs under 55 meters. You should also buy switches with open SFP slots to ensure you can expand with fiber later. Finally, the legacy integrator. If you are connecting a distant building using perfectly good older copper switches, the fiber media converter is the exact right tool for the job. A reliable network isn't built by buying the most expensive cable on the shelf. It's built by perfectly matching the physics of the hardware to the physical reality of the room.